So tonight's speaker is Naomi Rowe-Gurney on the topic of they might be ice giants. Apologies for the terrible pun. If you're not familiar with the band, look them up. Solar system science and the James Webb Space Telescope. So Naomi Rowe-Gurney is a planetary scientist focusing on atmospheres of the ice giant planets Uranus and Neptune. She's currently completing a PhD at the University of Leicester, where she gained her undergraduate and master's degrees. And she specialises in planetary atmospheres, spectral inversion, and radiative transfer. Her research uses data from the Spitzer Space Telescope to characterise the stratospheres of these two planets in preparation for the forthcoming launch of the James Webb Space Telescope, the JWST. And Naomi is an active member of the JWST UK outreach community, as well as being a passionate communicator of astronomy and astrophysics. She's an advocate of women in science and the benefits of intersectionality in science culture in general. She taught physics in China for 2 years, where she set up the Shanghai Roller Derby League. And if you think that's a little bit off topic, you might be interested to know that her UK roller derby team was called the Dolly Rocket Rollers, and her nickname was Afronaut. In recent years, Naomi has worked with NASA and was featured on the BBC's flagship astronomy programme, The Sky at Night. And last month, she was featured in the online magazine Womanthology. She's authored or co-authored almost 50 papers and is a featured scientist on the absolutely wonderful Discovery Diaries website aimed at inspiring primary age kids to engage with STEM/STEAM topics via the arts. And if you're not familiar with STEM and STEAM, science, technology, engineering and mathematics, and then we stick in the A for arts. Finally, in breaking news, although there is one more stop press news that I am not going to reveal, I'll leave that to Naomi. Naomi has just applied to join the European Space Agency's astronaut program. Naomi, if you are selected, will you come back and tell us all about it?
Yeah, of course. Promise.
Oh, wonderful. Okay, so you heard it here first. We might have our first real astronaut speaking on PubSci. I'm going to turn off my microphone and camera. Naomi is going to share her screen. Ladies and gentlemen, please put your virtual hands together for Naomi Rowe-Gurney.
Thank you so much. Wow, what an introduction. Crazy good introduction. Right. Hopefully everyone can see that. So, right. So yeah, I'm going to be talking about the James Webb Space Telescope and what it's doing for solar system science. And yeah, it was Richard's idea for the title, so I can thank him for that. So this is what to expect from my talk today. I'm going to start by explaining what Webb is, its use for solar system science, a bit about my research, which is on the ice giants Uranus and Neptune, and outline how Webb is going to advance ice giant science. And then hopefully I'll update you on where Webb is now. So what is the Webb? So the James Webb Space Telescope is an orbiting infrared observatory. It has a 6.5 meter primary mirror made of 18 separate movable segments, 4 scientific instruments housed at the back of the mirror, tennis court sized 5-layer sun shield, and all of this is going to be stuffed into a rocket launched into space and slowly unfold itself as it approaches its home at the L2 Lagrangian point. The aim for the end of this talk is that you'll understand what on earth I just said. So basically it's big, it's really complicated, but it's also the future of astronomy, and it's the premier observatory of the next decade. So it's going to serve thousands of astronomers worldwide. Building it has already been an international collaboration between NASA in the USA, the European Space Agency, including the UK, and the Canadian Space Agency. So the main job of any telescope is to look at distant objects, gather light from those objects, and it will focus it either into your eye or like a telescope at home, or into some kind of instrument or multiple instruments if it's bigger. So Webb is unique because it's the first ever space telescope with movable mirror segments. And they need to be movable because we need to fold up the telescope because it's so big to put it into the Ariane launcher. And each segment can be moved independently to manually focus the light into the central detector and back into the instruments. And we'll get to those 4 instruments later. The easiest way to explain Webb is to directly compare it to the world's favorite telescope, which is the Hubble Space Telescope. Hubble was launched back in 1990. It celebrated 30 years in April last year. And since then, it's had over 1.3 million observations. And it's produced beautiful images like the ones you can see here, examples of amazing, groundbreaking solar system science. It's observed Mars all the way through to Neptune, plus their moons and even more. And it's discovered 5 new moons of Pluto. It observed multiple impacts at Jupiter. So imagine what Webb can do with even better technology. So how is Webb better than Hubble? So for telescopes, bigger always means better. So this animation shows the relative size between Webb on the left and Hubble on the right. And the larger mirror of the James Webb, 6.5 meters in diameter, has more collecting area for light, which means it can look at dimmer, smaller, colder, more distant objects than Hubble. And there's even a person there for scale. So you can see both of these machines are huge. So a major difference between Hubble and James Webb is what wavelength of light it looks at. So Hubble is mostly visible light. So what we can see with our own eyes is what Hubble mostly sees. And when we split light using a prism into a rainbow, then towards the red end, we stop being able to see the light and we start being able to feel it as heat. And that's infrared. And Webb looks at heat like we look at light. So it's useful for scientists for lots of reasons. So in the video just now, you've seen a nebula. So that's lots of gas and dust in space. And you first see it in the visible. And then here we can see it in the infrared. And you can look through the cold gas and dust to see those hot stars forming inside. So you can see it invisible here. You can't see through that gas and dust, but as soon as we turn into infrared, you can see through it and you can see those stars. And for solar system science, it's also really useful because we can do the same thing. We can look through gas and dust. So we can look beneath the clouds of planets like Jupiter that you can see here and see what's happening underneath those clouds. And because we're looking in the infrared heat, it needs to be kept cold. And Earth is really warm, so we need to be as far away from Earth as possible. Hubble, for example, is only at 570 kilometers away from us in a low Earth orbit, whereas we need to take it 1.5 million kilometers away to the L2 Lagrangian point. And a Lagrangian point is just a gravity well. So it's where the spacecraft can hover and stay in constant communication with Earth as we both travel around the sun. And there is a downside to it being further away. Since launch, Hubble has had 5 space shuttle missions to carry out repairs and upgrades. And there's no way that we can do that when it's 1.5 million kilometers away. So it's a bit scary for engineers. They have to get it right first time. We also have to keep it cold. We keep it cold using the huge sun shield that's on the back as well. So that the big tennis court sized silver thing, that's also used to keep it cool. That's always facing towards the sun. So when we think of Webb, we think of astrophysics and cosmology, distant galaxies and the Big Bang. That's the kind of stuff that you'll see in the news. Whereas obviously we're more interested in the solar system, but it has 4 major science themes. So first, light is where it looks back over 13.5 billion years to see the first stars and galaxies forming in the universe. Galaxies, it helps us to understand how galaxies assemble over billions of years, and protoplanetary systems. So it sees through the dust and looks at where stars and planetary systems are being born. And then our last one, so the one that we're interested in, is the solar system, looking at planetary systems. And that's what I'm going to be talking about in this next part. So not many people know that the James Webb Space Telescope is going to be looking at the solar system. Most press is obviously about the astrophysics and cosmology questions, but a lot of the coolest science is going to be in the solar system. I'm a little bit biased, but I definitely think that that's true. So what in the solar system is Webb going to be able to look at? Basically everything from Mars out. It can't look back towards the sun because it will burn out all the instruments, but as long as it's not facing the sun, it can look at it. And that's actually more difficult than it sounds. It's going to be able to look at planets, moons, asteroids, Kuiper Belt objects, and comets. And for a telescope that's mainly looking at distant objects like galaxies and stars, they're dim and also very stationary on the night sky, whereas everything in the solar system is relatively bright compared to that, and also fast moving. So engineers have to overcome these obstacles to make solar system science possible. They have to make sure that Webb can track objects moving quickly, and also make sure that the instruments don't break when they look at something bright. So if we start with our closest neighbor, which is Mars, one of the fastest objects that Webb can track is Mars, and it's also one of the brightest because it's so close to us and so close to the sun. And we're able to observe it when it's at its dimmest, which is around every 2 years. And when we do, we can make global maps of Mars like the one shown on the right. That shows us what it's made of and what the atmosphere is like, and it can help us answer the really big questions that we're looking for on Mars, which is what happened to make those ancient lakes and oceans and rivers on Mars dry up? Could Mars have ever hosted life? And was it recent or was it in the distant past? And also things like what causes the Martian global sandstorms, like the one observed in 2018 that you can see in the image. And that's especially important if humans are ever going to visit, because we don't want to lose a Matt Damon again. So this GIF here is showing from The Martian, the movie, and it's not scientifically accurate representation of how we would lose Matt Damon because the atmosphere isn't thick enough to have that kind of impact. But it is true that we could lose him in some kind of dust storm. So it is important that we know what's happening. So if we go further out in the solar system to the giant planets, my favorites, Jupiter and Saturn are really big and really bright, but we can still observe them in most of the instruments on the James Webb. We can look through their atmospheres, like I talked about, and see what they're made of. We can see what the weather is like and why it's like that. And we can even do things like target Jupiter's great red spot to find out how it's working and what it's doing at the time. We can look at rings of the giant planets. All of these images here are from the VLT, the Very Large Telescope. And it also includes my favorite planets, the ice giants that I'm most excited about. And I'll come back to them later when I talk about my research. But I've included actually this image here by Roman et al. That's my colleague Mike. And this is the first ever observation of Uranus's rings at these wavelengths. And that was only last year. So still very new stuff coming out. So it's not just planets, but also their moons as well. The moons of the solar system are some of the most interesting bodies. Moons like Europa and Enceladus are really cold, but deep within them, they could have these subsurface oceans that may contain life. And Europa, for example, is the second largest reservoir of accessible liquid water in the solar system after Earth, which is amazing. And then we've got moons like Titan, the only body in the solar system where there are rivers, lakes, and oceans like there are on Earth, but instead of being made of water, they're made of methane. And this image here is from Cassini infrared instrument, and that's able to penetrate the haze and reveal the surface, just like James Webb is going to be able to do. So if there's life on Titan, then it's going to be not as we know it, but it could still be there. Then there's asteroids and comets, otherwise known as primitive bodies. And they're of huge scientific interest because of the leftovers from the formation of the solar system. And asteroids and near-Earth objects like Eros in the video here are really small and really cold, so they're very faint and hard to observe, especially from Earth. But Webb is going to be able to do that. And they contain answers to some of the biggest questions. So they're going to help solve mysteries of the early solar system and planet formation. And maybe these bodies even brought life to Earth. We might be able to find out a bit more about that. So other forms of primitive bodies are the Kuiper Belt objects, or TNOs, or trans-Neptunian objects, as they're otherwise known. Asteroids are mostly in the asteroid belt between Mars and Jupiter, but KBOs are beyond Neptune in the Kuiper Belt. And they're much colder and further away than asteroids, which means they're much harder to observe. But Webb is going to be able to characterize every known KBO we've seen to date, and hopefully find some more. And you might think you don't know any KBOs, but actually Pluto is considered to be a KBO, and some of the other dwarf planets. And also the largest moon of Neptune, Triton, that is considered to be a Kuiper Belt object that's been captured by the gravity of Neptune. So yeah, Webb is going to be able to look into the coldest parts of our own solar system, but it's also going to be able to look even further. It's going to help solar system science in a completely different way by looking at exoplanets. So exoplanets are other solar systems in our galaxy, and Webb's going to be able to look at them directly, like the video shown. So this video comes from 7 years of data from the Keck telescope in Hawaii, and the Webb images are going to be even better because we don't have to look through our atmosphere. So the questions that we answer in our own solar system are going to help with answering questions about other solar systems, and also vice versa. So it's a win-win situation. So in the next part, I'm going to be speaking about my research. So speaking of exoplanets, the most common form of exoplanet discovered so far is a Neptune-like or an ice giant-like exoplanet. And so everything we know about ice giants is from our own ice giants, Uranus and Neptune. So my research uses the Spitzer Space Telescope to look at the atmospheres of both planets. So Richard said a little bit about this, but I did a 4-year integrated master's at the University of Leicester, took a break for 5 years, and then went back to Leicester for my PhD, and now I'm in my final year. And my thesis is looking at the atmospheres of the ice giants. And that's why I'm now involved with Webb, because the ice giants are some of the most important solar system targets. And that's because they're so cold and so distant, they're exceptionally difficult to look at from Earth. And my research helps to find the questions that we want to answer with Webb. And actually, I graduate this summer, hopefully, as long as I complete my thesis, which I'm deep into now. And I'm going to be going on to work in the USA at NASA Goddard directly with the James Webb Space Telescope, doing being an ambassador of solar system science. And I'm not allowed to officially announce that yet, but I can tell everyone here. So the ice giants are interesting because we actually know very little about them. So the title of this talk from Richard was very apt, because we don't actually know if the ice giants are even icy. There's a whole string of papers that talk about how they might actually be rock giants instead. And that's because we have only been to them once. So we visited them with the Voyager 2 in the late 1980s. It did a flyby of Uranus in 1986, and then it did one of Neptune of 1989. And I'm talking a flyby, it literally just went past. And all of the images that you think of Uranus and Neptune, they've probably been taken by Voyager 2 in the 1980s. So everything else has to be done from remote sensing, and that's what I do. So the two ice giants are these two images here taken by Voyager 2. They have a lot of similarities. That's why they're both ice giants. So they are similar size. They're smaller than Jupiter and Saturn, but they're bigger than Earth. They're made of the same kind of stuff. They're hydrogen helium based, and there's no surface like on Jupiter and Saturn. And we think they have the same origins, but honestly, we don't know. They both have rings and moons. They're both blue due to the high concentrations of methane in their atmosphere, but there are also a lot of differences between them. They have different axial tilts, different internal heats. That means they have different activities in their atmospheres, and they also have different satellite systems. So both are really interesting for us to study. But people often define Neptune as our typical ice giant. That's why exoplanets are called Neptune-like, whereas Uranus is seen as the unique one, or the weird one. That's why it's my favorite. So let's start with Neptune. Our typical ice giant. It takes 164 Earth years to orbit the sun, and the atmosphere is extremely dynamic. This video here on the right is from Voyager 2 back in 1989, and you can see the great dark spot there as it comes around. And on the left, you can see some Hubble images. So this is remote sensing, and they show how variable the atmosphere is over short timescales. So those clouds are constantly there, but they're constantly changing location and strength. And we'll come back to why that's important later. Yeah, it has the fastest winds in the solar system, over 500 meters per second, which is really, really fast. And then we have Uranus, my favorite one, the weird one. So it has an 84-year orbit, so it's closer to us and therefore closer to the sun, than Neptune. But the atmosphere is actually colder, and it has a 98-degree obliquity, which means it's rotating on its side. So when Voyager 2 visited, it was at its solstice, which means that you could only see the pole, and the pole is kind of rotating towards us, like in the video. That video, again, is from Voyager 2. And in 2007, that's when there was the equinox, and the equinox, it looked like the top video where the rings edge on, and it's rotating like that. So it changes during its trip around the sun. And people think that maybe Uranus is different to Neptune because it was hit by something very early on in its existence, and that's why it's colder and also on its side. So my research uses the Spitzer infrared spectrometer. Spitzer was launched in the same generation of telescopes as Hubble in 2003, and it was decommissioned only last year in January. It was in an Earth trailing orbit, so it's following us around the sun, and it was pretty small. So the mirror is less than 1 meter across, and the infrared spectrometer that I use is similar wavelengths to one of the instruments on the web, which I'll come to later. But it's been used to observe both of the ice giants, and I use archive data that's between 2004 and 2007. And the spectral resolution is pretty good, but we don't have any spatial resolution, which means we don't get any pictures, and instead we get spectra like this. So this is an example from Uranus in December 2007 during the equinox, and this is the data that I'm working with. So the bumps and troughs show what the atmosphere is made of, what the temperature is, and also how it changes at different depths. And it can even tell us about the weather and the circulation sometimes. So data is taken at different times. And as time passes, Uranus rotates and shows us different sides. So my investigation splits up different longitudes, the different detections at different longitudes, to see if anything is changing between them. So the plot on the left shows the different longitudes the observations come from. So there's a nice spread across the 360 degrees as it's rotating. So do we see a difference between the longitudes? Yes, we do. So we see a consistent variation very clearly. The right plots show the difference in the radiance for an entire range of data. And the longitude 3 in green, you can see it's dimmer, so its variation is down. And the purple one, longitude 4, is much brighter. So something is changing. So to look closer, to try and visualize what's going on, we look at each chemical species in the spectrum. So each bump and trough corresponds to a different chemical. So it's shown in this picture here by the bands in the different places in the plot. So each species contributes to a slightly different height in the atmosphere. So everything above the tropopause is the stratosphere, and everything below the tropopause is the troposphere. So as an example, methane here, it contributes to the stratosphere. And then these two species are hydrogen and helium, and also CH3D, which is a type of methane. They contribute deeper down in the troposphere. So what we can do with this information is we can plot the variation of each species as Uranus rotates. So we can see something happening here. We can see that the tropospheric species, so the CH3D and the hydrogen and helium, they don't show any variation across those 360 degrees as it's turning, whereas the stratospheric methane shows a considerable variation. It's changing up to 15% as it rotates. And we see that same variation in all the stratospheric hydrocarbons at varying levels. So we know we have a longitudinal variation in the stratosphere, but we don't know whether it's a variation in temperatures or in gas abundances. Or even what physical process or feature is causing it. But there are different ways to find clues. One way we can find clues is to get some kind of spatial resolution, so get some pictures of what's going on. And we're actually extremely lucky that some images from the Keck telescope in Hawaii were taken 4 days before the Spitzer data that we're looking at. And I'll talk about them more in a moment. But another way is modeling the variation. So we use a type of software called the Nemesis software, and it does optimal estimation retrievals of the data. So the left plot shows a retrieval or a model against the data. We modeled each longitude separately and found that it's realistic that it could be a change in temperature only, because the right plot shows the changes in the temperature needed for the variation over the entire depth of the atmosphere. And only around 3 degrees difference is necessary to cause the changes that we see in the spectrum. So let's go back to these images. As I said, this data is from the Keck telescope in Hawaii, and they're in the near infrared, so not the mid infrared anymore. And they're sensing pressures around the tropopause. And we're seeing 2 opposite hemispheres in this data. So on the left, we see about 80 degrees longitude, and on the right, we see about 230 degrees longitude. And we have 2 one active and one dormant. So we have some activity, some cloud activity happening at 80 degrees, but nothing seems to be happening at 230 degrees. And the active side corresponds with the coolest stratospheric emission, which could make sense if this activity is bringing up cold gases from below. So we could be seeing a change in temperature due to that. Another thing we can look at is data in the mid-infrared, so the same kind of wavelengths as Spitzer, and this is from the VLT in Chile, but it's from 2009, so slightly different time. And it shows an apparent stratospheric spatial variability happening. So we're seeing a variability in different bands of multiple instruments at multiple times. So we could be seeing the source of longitudinal variability. But do we see the same thing at Neptune? Is this something that happens at Neptune as well? Strangely not. So we see a less than 2% variation across the same species in 2005 at Neptune. And before I mentioned that Neptune is highly variable and very dynamic. So we actually hypothesized the complete opposite. We thought we would see more variation at Neptune. But what we think we're seeing is that Neptune is too dynamic. So one feature on Neptune doesn't stand out against all of the features that are there. So the hemispheres will look very similar as they're rotating. But we actually won't know what is happening. We won't know why it's happening until the James Webb Space Telescope. So that's why all of my work is geared towards getting the James Webb Space Telescope. So what can Webb do to help us find out more about the ice giants? So major advancements from Spitzer is going to be 6.5 meters. Remember, it's a massive step up from Spitzer's 0.8 meters. And we can see in the right plot the minimum flux detected by various instruments within an acceptable signal to noise ratio. And the two Webb instruments are in blue. And basically it's showing that they're more sensitive and they also have better coverage than Hubble, Spitzer, and Sophia and Gemini, which are Gemini's ground-based and Sophia is in a plane. So yeah, we're more sensitive and we have better spectral coverage and better spatial resolution than Spitzer and better spectral resolution than Spitzer and the ground-based telescopes. So what about Earth or ground-based? Earth ground-based stuff, they're huge. There's like, they're 10 plus meters in diameter, so much bigger than James Webb, which is 6.5 meters. And we have, I can hear somebody chatting. Okay, sorry, I muted you, Janice. And so what about ground-based? So they're huge. And there are 3 of these images are from the VLT in Paranal in Chile. So that's the image in the background. And there is one image from the Keck telescope in Hawaii as well, and it shows how detailed we can see from the ground, even in the mid-infrared, which is notoriously difficult from the ground. And it's difficult because of atmospheric absorption. So between 5 and 30 microns, which is the super interesting range for us for temperature and composition of atmospheres, we get good spatial resolution because of the huge mirror sizes, but because of absorption, you get really poor spectral resolution. You can see maybe one wavelength, one band at a time. So we've seen we can currently frequently have to choose between finding out what something is made of and what something looks like. For example, Uranus, with Spitzer, we can see the spectrum, and with the VLT, we can see the picture. But what's exciting about Webb is that we're going to be able to do both. So Webb is going to be able to look at information and image using something called an IFU, or an integrated field unit. And that means that each pixel in an image also has an associated spectrum, and excitingly they're called spaxels, which is really cool. So that's really extremely exciting for scientists involved for the ice giants. And our team at the University of Leicester have access to guaranteed time observations, and GTOs, as they're called, are when you observe something in the first 12 months of operation. You're guaranteed to get that time. And there's a fair amount of allocated time, enough to cover 3 longitudes and to map 360 degrees of both planets. And both will get observed in the mid-infrared, and Uranus will also be observed in the near-infrared. So let's go back to those 4 instruments. The 4 instruments aboard the telescope are housed in the ISIM, or the Integrated Science Instrument Module that's behind the mirror. So you've got the near-infrared camera, or NIRCam, the near-infrared spectrograph, or NIRSpec, the mid-infrared instrument, Miri, and the fine guidance sensor, or the near-infrared imager and slitless spectrograph, or FGS NIRIS. And in GTO, or the guaranteed time observations for the ice giants, we'll be using both Miri and NIRSpec specifically. So this is Webb imaging and spectroscopic capabilities across the whole range for all the instruments, from 0.6 microns in the near infrared all the way through to 28.5 microns in the mid infrared. So for the GTO, we're using the NIRSpec and Miri, so we basically have the entire spectrum, and we're specifically using those for those IFUs, so to be able to have those spaxels. That's what's interesting for the ice giants. So let's look at NIRSpec. So NIRSpec provides spectra from 0.6 to 5.3 microns. so in the near infrared, and it's being used for Uranus in the GTO because it's mostly being used to look for evidence of the magnetosphere. So it's looking for a chemical called H3 plus that's formed really high in the atmosphere and is a sign of auroral activity, like the northern lights on Earth that you can see in the video. And the plot on the right shows the planetary spectra compared to the saturation limits of NIRSpec. So everything below the black lines can be observed with NIRSpec IFU. So all 4 giant planets are observable, which is really exciting. And now Miri. Miri is the best instrument. I'm biased because it's a UK-led instrument, and the University of Leicester has done a lot of engineering on it, and a lot of people in the UK are really excited about this instrument. A lot of people worldwide are excited about this instrument, and I think it's the most exciting instrument, but obviously I'm biased. But the Miri medium resolution spectrometer is it has 4 IFUs. It has similar wavelengths to Spitzer, but better spectral and spatial resolution than Spitzer. And you can see the size of all 4 in the bottom plot against Uranus and Neptune. So that's what it's going to be looking at. And it literally looks like the James Webb was made to look at the ice giants, even though it wasn't. It's just serendipity, but it's very exciting that they're so perfectly built for it. And again, the right plot shows the MRS filter saturation limits in the red curves. And so we have to be careful with Miri because Jupiter and Saturn sometimes are too bright for it, but Uranus and Neptune are observable over the entire range. So that's very exciting. So with these instruments at these wavelengths, these are the main goals of the GTO. So what we want to find out using that guaranteed time observation time. So we still know so little about both planets that these are very broad goals. So we want to generate spatially resolved global spectroscopic maps of both planets, and that will be for the first time ever. Nobody's done that before. And these will reveal contrasts in atmospheric temperatures and chemical traces. For example, at Uranus, we're going to be able to look at how the tilt affects it, get a full chemical inventory finally, because Neptune is much colder, it's much harder to observe. And we're going to be using NIRSpec again to look at the H3 plus. And then for Neptune, we're going to be investigating why it has that extremely dynamic atmosphere and how that affects everything. And then one of the most important things that we'll do is the results for both Neptune and Uranus are going to be compared to each other so we can understand the differences between the 2 planets and why Neptune is considered our typical one and why Uranus is our weird one. Why are they different? We don't know. So the last section I'm going to go through, I thought it would be good to update you on where James Webb is now. So everything is running to schedule with the telescope. As of December 2020, they did the final tests and deployment of the sun shield, and that was all a success. Proposals are in from the science community asking for time on the telescope for cycle 1. That's all been allocated now. So the first stages of science are being prepared for. And then at present, the deployment tests and final stow are underway at Northrop Grumman's California facility. That's where it is right now. And despite COVID, loads of milestones have been reached over the last 18 months. For example, this month is the final time they tested the opening of the mirror. Remember that mirror has to fold, and the launch date should be Halloween this year. But there could be a problem. And this is recently, like 2 weeks ago, they have said that the last 2 launches of the Ariane 5, so this isn't a problem with the telescope, this is a problem with the Ariane 5 vehicle that it's going to be launched in. And they were very adamant that they were going to be on the Ariane 5 and not the Ariane 6, because the Ariane 6 is new and the Ariane 5 is reliable, and now I guess somebody's kicking themselves. So yes, in the last 2 launches, the vibrations went well above acceptable limits, and that could be disastrous for Webb because it's made so it can withstand the vibrations that the rocket usually gives. And if it goes above that, then it could rattle things out, and Webb really needs to be, perfect. And they're doing tests now, but they could end in some kind of delay. They don't know whether it's going to be weeks or months. I have no idea, but hopefully we'll find out soon and it won't be too much. So it's supposed to ship to French Guiana's Isa spaceport in about August. And there are 55 days of launch site processing once it gets there. And that means it's going to get stuffed inside this Ariane 5 nose cone, and that's what it's going to look like inside. So that what it looks like folded up and stuffed inside that nose cone. So that's where all those vibrations come in. If it's really vibrating, then it's just going to vibrate to pieces and it won't be able to do what it needs to do, which is unfold. So after launch, it takes about 2 months to reach the L2 Lagrange point and cool to operating temperature as well. And that's followed by about 4 months of alignment, checkout, calibration, etc., before the proper science can start. And if everything goes to plan and Ariane 5 isn't a big delay, then the first release science should be dropped around May next year. So this time next year, we should be seeing the first science. But the most likely ice giant windows are in summer 2022. So we won't be seeing that until, about a year and a half from now. And more solar system science is being proposed for all the time. And it's hoped that these first observations from Webb are going to encourage more solar system science to be done with it. So yeah, I'm going to leave you with some links that you can visit for more information, and you can follow me on Twitter for updates on the ice giants and also on Webb. And yeah, thank you so much, and I'm really excited for your questions.
Marvelous. Wow. Thank you very much, Naomi. I think that was probably the highest number of acronyms we've ever had in a single PubSci. And if anybody is unclear about anything, do feel free to ask. That was absolutely fantastic. And yeah, I mean, there's a lot. I don't know how you managed to pack that all in. It may be like following up the James Webb into the Ariane rocket nose cone. It was all packed in there, and I suspect some people might want to unpack a few things in the questions and discussion. I don't. Did you explain the significance of the Lagrange points? By the way, I was dealing with an arriving pizza at that point, so I apologise, and I assume
it was a gravity well. Yeah.
Okay, that's cool. Yeah. So L1 and L2, lovely. Excuse me. I have to say, those who are regulars at PubSci will know that I always like to listen out for good fantasy band names. And I think we got 2 today. So thank you, Naomi. We've got Primitive Bodies and Spaxels.
Spaxels, yeah.
Spaxels, great. Obviously, totally different kinds of music, but yeah, we have 2 band names out of that. So
what kind of music is the Spaxels? I feel like electro.
Yeah, it's electro. It's electro pop, isn't it? Yeah. Yeah. And Primitive Bodies, I think it's kind of indie, probably.
Yeah, probably.
Yeah.
Not myself.
Yeah. So well, that's great. We're going to take a little break. Right. Well, I hope you enjoyed that. That didn't last long. So when Naomi comes back, here we go. Excellent. It says click to exit full screen. Let me exit that. Okay. So we have a few questions lined up. Janice, my cat stepped across my lap. I must have switched audio on. So we've got a few questions.
Picture of the cat, or it didn't happen.
Yes, absolutely right. Yes, this is the interwebs after all. Actually, I had not a question but an observation, which is the Kuiper belt is huge. I had no idea. It's massive.
Yeah, there's lots in it.
So one question I had, and the other clarification was you were talking about the VLT, very large telescope, not bacon, lettuce and tomato. That's a V.
Yeah.
But you were talking about sort of comparing the spectral emissions from Uranus and Neptune, and talking about the stratosphere and troposphere. Can you just clarify for people what that is? Because I don't know how many people will know what the troposphere versus the stratosphere is on Earth, and also, I mean, obviously, this implies that there is essentially weather on both those planets. So, could you say a bit about that, please?
Yeah. So the troposphere and the stratosphere are just two different layers of the atmosphere. So the troposphere is the tropopause is just like a boundary that they set that's between the two. So it's just like one layer is above this tropopause and one is below, and they set this this boundary by looking at the temperatures. So the temperature increases in the stratosphere and decreases in the troposphere. So, sorry, the other way around. It increases in the troposphere. So yeah, they said it like that, and then it's exactly the same as Earth, as it is for the ice giants and the gas giants, and it's the same here as it is there. The same kind of fluid dynamics happens on the planets. So you end up with like cells. So on Earth we have like the Hadley cell and things, where you have like currents of air that go around the globe and like carry things in different places. That's exactly what happens on the ice giants and the gas giants.
Can we learn anything about the atmosphere of Earth, and perhaps also the impact of temperature fluctuation in the climate of Earth by observing these planets?
It's mostly the other way around, because we don't have as much data. All the data is from Earth. So we know a lot about the ice giants because of how we study the Earth,
right,
rather than the other way around, just because of the lack of data. If we had as much data on Uranus and Neptune and the gas giants as we did on Earth, then of course we would learn a lot about Earth as well. But because we're looking at maybe 4 different telescopes that look at it, we can't really say.
Right. So at this stage, there are no learnings about climate change on Earth from observing those planets at this stage.
No, not really.
Okay.
Not at this stage.
So there's a question from Sam. Would a crewed mission to Europa be safe, and how many years off are we, if so?
To Europa?
Yeah, crewed mission. Yeah.
Crewed? Oh, a long way away. We're still a long way from Mars, even. So I think, yeah, not within my lifetime, at least.
Okay.
I don't think so. A while.
And there are only so many Matt Damons you can afford to expend. Matt Damon. Matt Damon. That's his his evil twin, isn't it?
Evil twin, Matt Damon.
Yeah, only so many we can afford to lose.
Yeah.
Okay, great. I actually thought it's really interesting when you're showing that video and pointing out that the atmosphere on Mars just is just not dense enough to blow people over like that.
Yeah.
Even though there are dust storms.
Picked up like a big heavy object and then smacked Matt Damon in the face. I don't think that's not going to happen. But you could get lost in it. You could get lost in it. It would be like a dust storm on Earth. Like pretty bad.
Yeah, fair. No, that's fair enough. I actually did read some comments on Facebook, more fool me, from people who objected to the claim that NASA had recorded sound on Mars from the I know from the rover. People trying to claim that the atmosphere is not thick enough to or not dense enough to actually sort of for sound to exist as we understand it, and therefore this was all fake because probably they hadn't gone. But I mean, there is an atmosphere. It is a medium.
Yeah, it definitely has enough for sound.
Yeah. Okay. So, question from Deborah. That was brilliant. That's not a question. That's a statement, and I think we all agree. What is the lifespan of the JWST?
Well, initially it's I think 5 or so years, but as with every telescope, it gets extended. So I can't remember what the Hubble was meant to go for, but it certainly wasn't 30 years. So you're looking at the same kind of thing where it will last for a lot longer. I mean, their aim I think is 10, but it'll probably be beyond that.
The Hubble is 30 years old. It's been operational for 30 years.
31 now,
That's
yeah.
that makes me feel really old.
Yeah. It was launched the year I was born.
That makes me feel even older. Thanks, Naomi. Um, Gosh, so only 5 years operational,
Yeah,
core
estimated.
operational lifespan. What was the budget, by the way? Do
Uh,
you know
uh,
that off the top of your head?
it cost $10 billion, around 9 point something billion.
So is that the Hubble or the? I'm talking about the Webb, but
Oh, that's the
yeah,
Webb. That's the Webb.
yeah. Oh, the Webb.
Yeah,
Okay.
I don't know how much Hubble cost.
Yeah, 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 yeah.
That was a
I
while
know.
ago, so it
And
was
we'd have to
old money.
scale it up. Yeah,
Yeah,
yeah, yeah.
but yeah,
Okay.
the Webb is
So
ten
hang on,
billion dollars.
$10 billion.
Yeah.
So you could build 3.7 webs for the cost of the UK test and trace system.
Yes. Thank you.
I'm not making any or asking people to make any inferences from that. I'm just doing the maths. The rest is up to you. Okay.
And the European input to the James Webb was 300 million, about around
Okay.
just over, I think, $300 million, 300 million euros.
300 million years. Okay.
Yeah.
That's a fairly small stake overall.
Yeah.
I mean,
well, the Canadian Space Agency and NASA's got
yeah.
a much bigger budget than we do. So.
Yeah. Talking of NASA, you kind of just did a throwaway about working for NASA. Can I encourage you to, obviously you're not allowed to officially announce it, but can I encourage you to go into that a little bit more?
So I'm going to be working with the solar system like a team at NASA Goddard. They do like all of the solar system stuff that I talked about. So basically, I'd be like an ambassador for the solar system, like liaising with people all around the world who want to do solar system science with Webb. That's the plan.
That's fantastic. Are you going to be based at the Goddard Space Center, or are you going?
Yes, I am moving there in October time.
That's fantastic. Oh, so possibly you're going to get a sort of front row seat at sort of well, not at Capcom, but at presumably a NASA live feed of the launch, maybe.
Maybe, I don't know. Even my boss in NASA is struggling to find like a way to get to watch it. So.
Well, fingers crossed. Okay, it gets more and more exciting. Question from George. Hello, George. Could information obtained by James Webb at some point be used for terraforming another planet?
That's a good question. I'm sure it could. The information it gets from Mars and also the moons. Those are like our closest neighbors for terraforming. Definitely could be useful. And what James Webb does that is better than like the probes that it sends and stuff is that it can get this global information. So it can look at the entire surface at the same time. So that's what is exciting about it. It can see through any atmosphere, but it can also see the whole planet at the same time, which is useful for obviously lots of scientific interests.
Yeah. An interesting question from Giles. Hello, Giles. That's my brother, by the way. Who studied physics at Exeter many moons ago.
Really?
Yes, he did. What drives the activity on the ice giants? What is the source of their energy?
So the sun mostly. But for Neptune, there is an internal heat source. So just like on Earth, there is some kind of core, like molten core that's happening. Whereas on Uranus, weirdly, we still don't know 100% why, there is negligible heat inside it. So all of the energy that we see comes from the sun in the atmosphere. And as I said in the presentation, it could be because a large object hit Uranus when it was first being formed, and that basically turned the planet inside out and got rid of all of its internal heat. But some people also say that it could be because we're not seeing the heat. It is there, but it's kind of trapped under this layer somewhere, and we're not seeing it with our telescopes. So there's no way to know, really.
So there could be a kind of thermal inversion, essentially, where it's all sort of trapped below a layer. And obviously the Earth, we now know or suspect, has also a lot of heat energy from radioactive decay. Is that something we know about or could find out about from the Webb for the ice giants?
Radioactive decay of what, sorry?
So my understanding is that there's a radioactive activity, radioactivity in the core is partly responsible for the heat energy that is output from the core of the Earth.
Yeah.
And is that something that we know about or could find out about from the Webb, or are we really looking at the atmosphere, so are unlikely to find that out from the Webb?
Without a probe, you wouldn't be able to go much deeper than what I study, which is like the deep troposphere. So there's no way, like at a certain point, the clouds become too opaque and you can't see through them with any of those wavelengths. So you can with like microwave, you can go a little bit deeper, but still it's only maybe like a few hundred bar. So you're not getting to those deep levels. So a lot of the science that comes, which is deep atmosphere, is usually it's usually like the conclusions have been gotten from magnetic stuff. So I was talking about the H3 plus, that's going to tell you what's going on inside, and then they're still using data from the Voyager 2 stuff to look at the magnetic shift and what's happening inside. Like the gravity of the planet also tells you what's going on deep within.
Right.
We need a mission.
A personed mission, a populated mission.
A person. We don't need
a probe
people.
mission.
Just a probe mission.
Just a probe.
Yeah.
Okay.
Any mission. A robot will do.
Any mission. So I've never been entirely clear. So the gas giants actually do have a rocky core, but they're largely gas. Is that correct?
All of them will have a rocky core of some kind.
Right.
But when I said rock giants, I meant that so at the moment they think that there's a rocky core with like an icy layer around it. So ice water around it that it does some weird stuff as you get further down. Like it becomes like super ionic and becomes really creepy and like black ice type stuff. But what they think it might be, because of all the gravity measurements they've had, it could be that it's just rock and then gas rather than it being gas and then water. So
okay.
There's definitely always a rocky core.
There's always a rocky core. Okay, because of course the term ice giant, is or particularly gas giant is quite misleading for without an explanation. And the gas is largely hydrocarbon. You're saying so, methane and
hydrogen
acetylene.
helium is the main constituents of hydrogen helium, and then methane is like a big constituent. That's why they're blue.
Right. Okay. So a second question from Giles. What limits the lifespan of the telescopes? Money, engineering, or something else?
Usually it's a combination of all of them. The lifespan of Spitzer, for example, was so with infrared telescopes, you usually have to actively cool them. You have to make them cold by using a cooling agent. So for Spitzer, it was liquid helium, I think. And so when you run out of that coolant, you can no longer use the instruments that needed that coolant. So for example, my instrument, the infrared spectrometer, the coolant ran out and you couldn't use it anymore. You could only use another instrument. You could use the IRAC instrument, but you couldn't use the IRS instrument. So
right, and presumably there's going to be an energy source which is going to be I can't remember what they're called now, but those sort of like, small nuclear electricity generators.
Yeah, they can run out of power too, but usually it's coolant.
Right, it's the coolant that runs out. So that's vented, is it? I mean, if it runs out, it's not just circulated; it must be vented into space.
But it gets hot, and then they have to get rid of it.
It evaporates. Oh, okay. Gosh. All right. There's a question from Kirsten that I don't fully understand. Kirsten, you just said asterisk just Naomi about pop vinyls, which you might need to clarify if you want to get an answer to that.
I don't own any vinyls. I'm terribly uncultured in that respect.
Yeah. I don't know. I don't know if it's like a subculture reference of sort of like your manga t-shirt or something. I don't know. Kirsten, you're into all the interesting things.
The Funko Pops.
Funko Pops.
Oh, if you can see them in the background.
Oh, wow. Who would have thought the resolution was that good?
Dark Side Rey from Star Wars. And the other one that I got is Black Widow, which came out way before the movie.
Wow. Kirsten, you recognized the
that was pretty impressive.
Focus packaging. That's really impressive. Any more questions, by the way? I think I had some more, but I think I've asked most of them. I mean, I suppose the question that many people will have will be about Pluto. So Pluto being a KBO. So you had one slide which showed the orbit of Pluto, which goes right through the Kuiper belt. So it's not it's quite an elliptical orbit. I didn't realize that it kind of slides. So it has some clear orbit and some orbit straight through the KPO. I mean, I don't know if I know this isn't your field, but I mean, how on earth does it survive? How does it actually get through? Because it's not much bigger than a lot of the other objects. And so one of the reasons that it was relegated to a dwarf planet, I believe, is because it hasn't cleared its own orbit. And yet you wonder how it even survives. Little Pluto basically spending sort of like a third of its life going right through the Kuiper belt, which just looks like like a dense.
It does look dense, but it's not dense. Like a lot of when they make these pictures, they make things a lot bigger than they are. But when you realize how sparse everything is in space, you realize there's no way. Like if you look at a picture of our galaxy with our solar system in it, it looks like we're going to hit every star in the galaxy as we're passing through our little area, but everything is just so sparse and so far apart from everything that it's very unlikely that we're going to hit anything.
Right. So that graphic was sort of showing the Kuiper belt more sort of dramatically. Graphically dramatically than it really is, because I think there's no way it can get through it. So it's okay. So it's much like sort of any sort of graphic of I know of the atoms and electrons in matter. You kind of how can light get through that without interacting with anything? Well, actually, they're very far apart.
Yeah.
Lots and lots of space.
Exactly the same.
That's really, really useful. Actually, so I mean, the Goddard Space Center has, it's like a quite a history. Sort of. I mean, seeing as you're going to be working there, do you want to just, sort of tell us one line about what the Goddard Space Center is, but I mean, actually, I don't know. I know all these names. The Goddard Space Center, the JPL, NASA. Can you give us all like a sort of a 30-second primer on sort of how NASA's set
How
up?
NASA works. I know how NASA works better than how ESA works, which tells you a lot about NASA and ESA. But NASA, they have these different places. There's loads of them. There's like 10 different sites all across the US. So JPL is in California and like Los Angeles area, and Goddard Space Flight Center is between Maryland and Baltimore and Washington DC in Maryland, and they're all run very differently. It's kind of like different sectors. So JPL, for example, isn't officially NASA, because NASA is a government organization. JPL isn't officially a government organization, whereas Goddard is in places but not in others. It's very confusing.
That's really interesting, because I think from what I've read, the culture of these places has been sort of very much part of their success. The kind of the mixture of this sort of official government mentality and the kind of the maverick thinking. So JPL's Jet Propulsion Lab, I mean, that shows how old the name is. And I mean, that's kind of really interesting, this mix of sort of maverick thinking and this giant, behemoth kind of institution. And it's the Goddard that you're going to be working for.
Yeah. So actually, NASA HQ, so the headquarters, which is like the government headquarters, is in Washington DC, which is nearby. So I guess Goddard is more science and less like government stuff. So the HQ kind of handles all of the things that they need to think about, and Goddard just does science. So
right.
Yeah.
And the JPL is where they largely kind of develop the actual sort of hardware, isn't it?
There's loads of stuff at JPL. JPL has, they're kind of like a university. They all have like the little departments that they have like a specialization in. So Goddard has a lot of stuff with instrumentation. JPL has a lot of like science-based stuff, but then it also has a lot of Mars rover stuff over at JPL. So it very specifically depends on what you're looking for.
Right. Okay. Brilliant. Okay. Just looking to see if there's any more questions. Oh, well, there's a lovely comment from Lisa, which is really informative. Even I have understood. Very interesting, Naomi. Even I have understood.
Thanks,
says.
Lisa.
Yeah. Okay. I mean, that's been absolutely wonderful. In a way, I've got 100 questions, but I've also got none, because it's just been so bloody brilliant.
Thank you.
If anybody has a last minute question, type it up. I mean, we're getting towards the usual wrapping up time, to be honest. Anyway, but I'm just going to make a few announcements. And if you can think of a question, especially if you don't normally ask questions or you haven't asked a question before, now's the perfect time. There are no stupid questions. There are no embarrassing questions. The only embarrassment is not asking that question when you leave Zoom and you go, oh, bugger, I wish I'd ask that, because I don't quite know.
You can always ask me on my Twitter as well.
Well, yes. So, I mean, what we can do is, Naomi, send me all the links you had on your last slide. And I always do a post-event email to everybody who signed up through Eventbrite. And so I'll make sure that goes out to all the Eventbrite attendees. And it also has all the links to PubSci and so forth. Obviously, for anybody watching on YouTube, you also have the opportunity to ask a question, but I can't see any there this time. So we've been PubSci, Science in the Pub, the virtual pub with real science, and we've been joined by Naomi Rowe-Gurney, and it's been an absolute bloody delight. So there's a question about recording the pub sessions when they start. Yeah, that's going to be very, very tricky to manage, but we're going to see about that. It's going to involve even more layers of tech, live hosting and live filming and recording. But for now, all you need to know is that there is no PubSci in June because we are going from the last Friday in May to the first Wednesday in July. And as I've said, our next PubSci is on Wednesday the 7th. Dr. Anna Morgan, Toxins, Friend or Foe. We are almost certainly, realistically, we're going to be doing that over YouTube again. If we do get to move to the pub, I will try and set up, if not a live stream, then a recording to put on YouTube. But obviously I can't promise because it all depends on technology and my capacity to manage multiple levels of technology. And oh yes, I'm moving at the end of July, so it's going to be interesting to see the little sort of static electric sort of fizzes coming out of my head for the August one. If you've not joined us before, then you can always go to pubsci.info, no www, just https://pubsci.info. You can also find us on Twitter at PubSci, PUBSCI. You can find us on Facebook. We're a group and a page. And you can, on PubSci.info, you can subscribe to the Google Calendar. You can subscribe for monthly emails so you get advance notification as soon as events come out. And you can hopefully join us one day this year in the pub you can see behind me, the Old King's Head in Borough, near London Bridge, where they serve fine ales and very good wines. So, we have one question from Diana. Who is this Diana Rowe? I've never heard of her.
It's my mummy.
Hello, Diana. You mentioned using 2 instruments for Uranus, but only 1 for Neptune. Yes, I did notice that. Why is that? Great question.
Politics. Basically, they have to ask for time on the telescope, and they have to justify the time scientifically, and you have to write like a whole proposal as to why you need the telescope for it, etc., and that denotes how much time you have on which part of the instrument. So for Uranus, they have never actually observed the magnetosphere before. So there's H3 plus stuff. They've never observed it on Uranus before, so they don't know whether there's a magnetosphere apart from the observations from Voyager. They've never looked at it from a distance because it's so cold. And they have seen it on Neptune, so they want to. Oh no, wait, sorry, it's the other way around. So on Uranus, they've seen it, so they know that they're going to see it when they look in the telescope. Whereas with Neptune, they haven't seen it before, so they want to. They don't want to do it unless they know they're going to see something, because it's such an expensive telescope. They're like, we need to know that it's there before we look at it, which is terrible, because how do you find something new unless you look for it? But unfortunately, politics
and money and time. Wonderful. Well, there's lots of people just saying thank you, and that was wonderful, which is...
Thank you for the cat picture. Loved it.
Oh, I couldn't download that. That's very strange. It was Sam.
It's great.
Yeah, but it's there. You've seen it.
Yes.
So the cat is real. the cat exists. Okay. That's fantastic. All right. So I think it's probably time to wrap up. In fact, it's the perfect time. It's 9:15. Naomi, thank you so much.
Thank you for having me.
That was absolutely brilliant. It was fascinating and understandable and really informative and really enjoyable.